Section 5.2, the characteristic equation. So let A be an n by n matrix. We learned from the section 5.1 that an eigenvalue of A is a scalar lambda that such that the determinant of A minus lambda I is equal to 0. So what is A minus lambda I? A minus lambda I is a matrix, and when we find its determinant, which is supposed to be a number, that number is equal to 0. That's what we want. So that will help us create a polynomial in lambda, or get a polynomial in lambda which we set equal to 0, and we try to factor and find the zeros of the polynomial, the zeros of the roots of the polynomial, which are the eigenvalues. The eigenvectors of A corresponding to lambda are the non-zero solutions of A minus lambda I times x is equal to 0. So the eigenvectors are solutions of this homogeneous equation, and this equation earlier, the determinant of A minus lambda I equal to 0, is called the characteristic equation of A. And as I just said, we will get a polynomial, and that polynomial called characteristic polynomial of A. Okay, so when we find the polynomial, we will get something, we might get something like this I am showing here. So from algebra, if you recall something called multiplicity of a root, that's what we are going to see here, or recall, that if a polynomial in x is factored like this, x square, x minus 3 whole cube, and then x plus 1. So the zeros or the roots of the polynomial are 0, 3 and negative 1, but their multiplicities are like this. So the 0 has the multiplicity of 2 because it's x square, and 3 has multiplicity of 3 because it is x minus 3 whole cube. So the multiplicity is the power or the number of times that factor appears in the expansion of the polynomial. And so there is a theorem here that A be an n by n matrix. Then A is invertible, means its inverse exists if and only if the number 0 is not an eigenvalue of A. So if the eigenvalues of A are all non-zero numbers, then the matrix A is invertible, then inverse can be found. The second is the determinant of A is not 0. So if the determinant of A is not 0, even then we can have the matrix A can have an inverse. Okay, so what are similar matrices? So this is a kind of maybe a new thing that you are seeing here, similarity or similar matrices. So let A and B be n by n matrices. So A and B are some square matrices of the same order. If there exists a matrix P, if there exists an invertible matrix P, so now notice here the inverse of A and B is not discussed here. So is A invertible? Is B invertible? We don't care about that. The important thing is this matrix P should not be invertible. Oh, it should be invertible. Okay, sorry, it should be invertible. Means its inverse must exist. Then if P is such a matrix that if we multiply the P matrix with A matrix in this order, P inverse A P, so that is important that P has to be in it has to be in this order, P inverse A P, and we end up getting the matrix P. If that happens, then we say that matrix A and B are similar, or matrix A is similar to matrix B. And if this happens, of course it will happen, So but now B is being multiplied by P, but in this order. Okay, the P inverse is on the right of B and P is on the left of B. Then A and B is similar to A. So A and B are similar matrices. In the same way, the B matrix is similar to A when you do this. So they are this changing A into this matrix or into the B matrix like that is called similarity transformation. So if it is given that there is a matrix A and it is converted into the matrix B using the similarity transformations, then you should know that there exists a P that behaves in the manner it is shown here. Theorem 4, if n by n matrices A and B are similar, so if we have two similar matrices, then they have the same characteristic polynomial and hence have the same eigenvalues and the same with the same multiplicities. Okay, so now how do we find the eigenvalues and eigenvectors? Well, eigenvectors you have already seen the method in the previous, I believe the previous section. So here we are going to look at this example of a 2 by 2 matrix. Okay, let me redo this. I think this is a little bit confusing here. So I'll rewrite. We will start by finding A minus lambda I. How do we do that? We get the A matrix, which is 2, negative 12, 1, negative 5. Okay. Then I say minus lambda times I. What is I? I in this case will be 1, 0, 0, 1. Which becomes lambda 0, 0, lambda. So I will just write it that way. Lambda 0, 0, lambda. And now I subtract. So I get 2 minus lambda. Negative 12 minus 0 is negative 12. 1 minus 0 is 1. And negative 5 minus lambda. So this is what is the A minus lambda. Now we know that determinant of A minus lambda I must be equal to 0. What does that mean? It means the determinant, which is given here, is equal to 0. And how do we expand? Remember, as the 2 by 2 matrices, so we expand, we get this equation, simplify, even factor, so we end up getting lambda is equal to negative 1 and negative 2. So now that is how we find the eigenvalues. Now for a 2 by 2 it's pretty simple, but for a 3 by 3 it becomes a little bit more work, and then 4 by 4 of course more and more work as the size of the matrix increases. So now to find the eigenvectors for each of these. So for when lambda is equal to negative 1, so A minus lambda I will become A plus I. So you can from the scratch do it, like have the A written here plus the I written here and then add them, or you can go back to the original matrix, the A minus lambda I that we found here. This is the A minus lambda I, and plug lambda is equal to negative 1 in there. So when you plug negative 1, you will get 3 here, negative 12 will stay negative 12, 1 will stay 1, but this will become negative 5 plus 1, so negative 4. So this is what we are getting. Now because I have to solve this equation for some x vector, and so I can augment the 0, 0 with the matrix and do our row operations. So these are the two row operations I did. One is this, and I will get that matrix. And from here x minus 4x2 is equal to 0, so that x1 is equal to 4x2. We can see from this row reduced form of the matrix that x2 is a free variable, so x1 is written in terms of x2, and then we go back and substitute in the vector x. X1 was a 4t and x2 was just t, so we get that. To factor out the t, so our eigenvector is 4 1. In the same way, here I have shown how to do the the similar process with for the lambda is equal to -2. Okay, now let's look at this next example. So it says find the eigenvalues of A. So we are just finding the eigenvalues, we are not finding the eigenvectors here. So we start the same way, A minus lambda I. So this is A and this is lambda I, and we end up getting this matrix. Now we have to find the eigenvalues, so we'll have to write the equation, the characteristic equation, which is the determinant of A minus lambda I is equal to 0. So I write it in the determinant form like this, and then I expand it. So here I have expanded, and then more expansion, more, and doing all the work, so we end up getting this polynomial. Now this is a cubic polynomial, so how do we solve that, or how do we, because there is no formula like a quadratic quadratic formula, we don't have a cubic formula here. So how do we do this? We do it like this. So we think of this as a polynomial which we have to solve. So we give it a name, p of lambda. So what we are going to do now, plug some numbers in there, some integers. We start with the smaller integers like 1, -1, 2, -2, and so on. So and notice here that only one term is negative, 3 terms are positive. So if we are picking small the positive numbers, we may not be able to get a 0, or if the positive number is large enough so that the lambda cube of that number is giving us a big number enough to compensate all these positive numbers, then but let's see, negative, if I plug in 1, I will notice I get this, which is not 0. Then I can try -1. So -1 will give me 1 plus 5, -39 plus 45. So this is also not 0. We can try 2, but I just thought maybe let me try -3, and I found that -3 did give me a 0 in the end. So what does that mean? It means lambda is equal to -3 is a root of this polynomial, and so that it means that x plus 3 is a factor of the polynomial. So we can write our the polynomial as x plus 3 times this. So where did I get this second factor? I did long division here, if you notice here. So I have also shown you the synthetic division. If you know one of these, that's what you need to use. If you don't know any, please learn. Okay, so this is the polynomial. Now this cannot be factored, so we have to use the quadratic formula. So we end up getting these values, 4 plus minus square root of 31. So hence the eigenvalues are -3 from this factor, and then these two other factors. So that's how we find the eigenvalues. Okay, example 3, find the eigenvalues and corresponding eigenvectors. So we have to find both eigenvalues and eigenvectors, but from the work you can see this is not that bad. So because there are a bunch of zeros in the matrix, so it makes things less complicated. Okay, anyhow, so we start again by A minus lambda I, which leads us to this, and then we find the determinant, which is pretty simple. It's just 2 minus lambda whole cube. So which means that lambda is equal to 2. Okay, from here we find that lambda is equal to 2. So now for lambda is equal to 2, we will have to go back in the A minus lambda I, and we can plug 2 in there for lambda in the matrix. We end up getting this matrix. So times x equals, remember we are doing so this is what we want to do. So here is my A minus lambda I, in this case will be 2i, and lambda plus 2i, wasn't it? No, lambda minus 2i, because lambda is equal to 2 is the eigen value. So A minus 2i is equal into x is equal to 0. That's what I have. But from this matrix we can see the only thing that we are getting is that x2 equal to 0. So what about x1 and x3? Because we cannot find them from here, so we say x1 and x3 are free variables. So I write my vector, the eigenvector x, x1, 0, x3, which can then be split up into two equations like x1, 0, 0 and plus 0, 0, x3, so that factor out the x1, x3, and our eigenvectors are these two. So we had only one eigenvalue here, and we have two eigenvectors for that one eigenvalue. So this is how you find the eigenvalues and the eigenvectors.